This is Engineering 246, Lecture 2, which corresponds with Chapter 2 in the textbook. So today, we're going to start looking at deformations of parts. Okay, and last week, I just want to recap a little bit. The previous lecture, we talked a little bit about this idea of stress, which, if you remember, I likened to the concept of a pressure that has a direction. Okay, so we talked mostly about normal stress, right? And the normal stress basically is due to forces that act perpendicular to the cross-section of a part. And then, of course, we talked a little bit about shear stresses, right? In the shear stress, the force is in the plane or parallel to the plane of the cross-section. All right? Now, today, as I said, we're going to start looking at deformations. Now, this is going to be quite a departure from statics, because in statics, we didn't care whether things deformed at all, right? We basically assumed that they didn't deform. And that was perfectly fine, because all we cared about were forces acting on those parts that we studied. In reality, okay, what we do know is that when you apply a force to any type of a structure, it's going to deform in some way. Okay, it might be a very minor deformation, something that you can't even detect, but it does exist. Okay, and in mechanics of materials, we actually start accounting for those deformations. Right? That does not mean that our structures are not in static equilibrium. They still are, right? But they actually do deform. A part can deform and still be in static equilibrium. You've all driven or gone across a bridge and felt that bridge move, right? That bridge might have flexed a little bit. It might have moved a little bit with the wind. It moved with the forces due to vehicles driving over it, right? And you felt those deformations. However, the bridge is still in equilibrium, right? Same thing with a skyscraper. We know that a skyscraper sways in the wind, but it's still in equilibrium, right? If it's not in equilibrium, it would move, right, and collapse. Okay, so deformations do happen, and what we're going to do in Chapter 2 is to start looking at those deformations. All right, now to put all of this in context for you, right, even though we looked mostly at parts that were in tension and compression last time, we also talked about this idea of a general state of stress. And I said that the general state of stress basically represents all the forces or all the stresses acting at a single point on a part. And since stresses act either perpendicular or parallel to surfaces, right, the best way to represent a point in 3D is to represent it by a square, because the faces or the surfaces of the square coincide with our coordinate direction systems, namely the x, y, and z axes. All right? So just to make things clear, in mechanics of materials, the only coordinate system we use is the Cartesian system. Okay? There are no polar coordinates, no normal tangential or radial transfers, anything like that. Okay? It is always Cartesian coordinates, hence the x, y, and z axes. Okay? So in a general state of stress, right, you could draw basically a cube to represent a point, and then we had said that on the cube, right, on every face, you had a normal stress, or a stress that's perpendicular to that surface, right? I'm drawing these so that they're all in tension, which would just mean these are all positive stresses, right? And then on each face, right, since we're using the x, y, z coordinate system, we're going to have two shear stresses. All right, and we talked a little bit, of course, about how we denote, right, these different stresses. Okay, so let's just bring deformations into this whole idea of a general state of stress. Okay, so this is my coordinate system. Horizontal is x, right? Vertical is y, and the axis that comes out of this page is the z-axis. Based on this coordinate system, right, these two stresses here are sigma sub x. These are the normal stresses in the x-plane, right? The x-plane is the plane, if you remember, that I said is perpendicular to the x-axis, and then these normal stresses are, of course, in the x direction. As far as deformations go, okay, what sigma x is going to do is stretch this cube so that it elongates in the x direction, right? So then, just to exaggerate, it becomes something like this, simply due to sigma sub x, okay? And then due to sigma sub y, it will elongate in the y direction, right? And due to sigma sub z, it elongates in the z direction. And of course, if these were compressive stresses, then instead of elongating, it would shorten in the x, y, or z directions. Okay? So normal stresses result in a part just getting longer or getting shorter, right? That should be fairly intuitive. How about these shear stresses? Okay, let me redraw my cube, and I'm just going to draw one of those shear stresses. Okay, so let's draw this one, the one on top here. Right, based on our coordinate system, right, you should recall from last time that this is going to be tau, right, that's our shear stress, y, that's my y plane, right, and then x, because it's acting in the x direction. And on the bottom face, the face on the bottom, I'm going to have something that's equal and opposite, okay, because I have equilibrium, so my forces must add up to 0. Okay, and actually, let me just point something else out here, right? If I just have these two shear stresses, these are both tau yx, okay? My forces add up to 0 due to these two forces, but, right, you recall from statics that these are two forces that are equal and opposite and offset by some distance. So they're going to give you a couple. They will cause this cube to rotate about the z-axis, right? So what that means is I need this and the one on the left face going downward. These are tau xy, if you remember. Right? Last time we defined these two as tau xy. Now, these two add up to 0, but they give me a moment, right? These form a couple with a rotation that goes counterclockwise about the z-axis, whereas the two up on top here, tau yx, give me a rotation that is clockwise about the z-axis, right? So what you can see is that if I combine these four shear stresses together, then I'm going to get 0 forces and 0 moments, because the couple on the top cancels out the couple on the bottom, all right? Hence, right, we had said last time that tau xy is equal to tau yx, right? And that's basically the reason why. Okay, these four values, the tau yx on the top, the tau yx on the bottom, the tau xy on the right face, the tau xy on the left face, those four are all the same value. Okay, and if they are, they have to be actually, right? Because that way we get 0 forces and 0 moments. All right, now with that out of the way, okay, what kind of deformation do I get from shear stresses? So I am going to go back to that cube with just the tau y-axis, okay, on the top and on the bottom. Try and imagine what these two stresses, or, you know, they could be forces if you want, all right, what these two forces on those two faces are going to cause this cube to deform into. Right? Can you imagine what this cube would look like if you were to apply large enough forces on the top and the bottom faces? You should get something like this. Can everybody see that? Right? Basically, if I look at this cube head on, it started off as a square, and then it became diamond-shaped. Okay, because there was this force pulling towards the right on the top surface, and then this force pulling towards the left on the bottom surface. Okay, so that's the deformation that shear or shear stresses give you. All right, so let's make that distinction clear. A normal stress causes elongation or shortening of your part. Okay, a shear stress causes a change in right angles. Okay, you see, you start off with a square here, right, with 4 right angles, and after you apply a shear stress, you no longer have right angles. These 2 angles become obtuse, these 2 become acute. Okay, so that's how you tell when you get shear stresses, when you have shearing in your part, is that right angles no longer stay perpendicular. Okay. And what you're going to see later on, okay, and I'll keep pointing this out, is I always suggest to students that when you're trying to tell whether a part is going to be under normal stress or under shear stress, right, then what you do is you draw a square on the side of your part, and then you try and imagine what shape that square deforms into. If it simply elongates or shortens into a rectangle, then you have normal stresses. If it changes angle, then you have shear stresses. If it does both, then you've got a combination of both types of stresses. All right, so that's what we're going to be looking at, okay, is these deformations that happen whenever we apply forces or stresses to our structures. So let's go back to our slide here. Okay, and last time, right, we said that instead of using forces in mechanics of materials, we now want to use stresses, because stresses allow us to compare parts even if they're different in size and shape. So when it comes to deformations, we want to do the same thing, okay? When I apply equal stresses to a structure, to 2 different structures that are made out of the same material, what I want is to have the same description of the deformation. Okay, so let me see if I can illustrate this for you. I've got a large column that's made out of steel, let's say, and then I've got a small column, and not only is it smaller, right, it's also made out of, it's also a different shape. And I'm going to apply the same stresses. So these are both steel. All right, these are both made out of steel, and I want to apply the same stresses to these 2 columns. What that means, of course, is this force 1 here, right, is going to be much greater than this force 2 here. Why? Because stress, if you remember, is this force divided by the cross-section, and since the large column has a much larger cross-section, in order for me to have the same stress as the smaller column, I have to apply much larger forces. So I have the same stresses, okay? Am I going to get the same deformations? If I just measure, right, how much both columns are going to elongate by, are they going to be the same values? Obviously not, because they're completely different size, completely different shape. I apply completely different forces to these 2 columns. All right, so that's not a good comparison. If I just measure how much each piece elongates, it's a very bad comparison. And the other thing is, we apply the same stresses to both of these parts. Okay, what I want is to have a description of deformation that gives me the same value for both of these columns. So how are we going to do that? People have found, right, in the earliest days, when this subject was first being developed, what people found was that if you go ahead and if you go ahead and take your original length, okay, and divide by, if you take the total elongation, or the total deflection, as we call it, that's this letter delta here, Greek letter delta, okay, if you take that deformation and you divide it by the original length, okay, then you do end up with a description of deformation that makes things comparable. Okay, And it's just like stress, meaning now the size and the shape of your part has no effect. So why is that? Right? Well, people have done all kinds of experiments, okay, and they've determined that this works out perfectly. So here's the original experiment that was probably performed. Okay, you start off with a column. You're going to look at 3 different columns. Okay, in the first column, the one on the left, okay, I start up with some original length L. Right, I have some cross-sectional area A. Okay, so A and L. And what I'm going to do is I apply some force P, and I note that I get some deformation delta. In the second column, okay, I make the area twice as large. It's going to be the same length, right? But the area now is going to be twice as large. And what I find is that in order to get the same deformation as in the first column, I have to apply twice the force. Okay, so you notice it's P here, and I have to apply 2P here. Or another way of looking at this, right, is if this column has twice the area of the first column, and I apply the same force P, what I'm going to find is that my deflection delta is going to be half of the original. Okay? And in the third column now, what I'm going to do is keep the same area as the original column on the left, but I double its length. Okay? If I do that and apply that same force P, now I get twice the deformation as in that first column. So here's another way of kind of looking at this experiment. Okay? Rather than applying a single force, what I'm going to do now is I start off with these 3 columns that are undeformed, and then on each column I start pulling from 0 force. And I keep increasing the force until I get to those values, right? P and 2P. And then what I'm going to note down, okay, is all the deformations at each step, right, as I keep increasing the force. All right, and what you can see is that you apply the same stress in all 3 cases, correct? We said we apply a force P in the first column, we had an area of A. In the second column, we applied a force of 2P, right, in order to get the same deformation, and we had twice the area. So sigma, again, is P over A, because I have 2 on both the denominator and the numerator. Okay, and finally, in the third column, right, it's the same force P and the same area A, so stress is still P over A. So I have the same stresses on both in all 3 cases. However, right, we had said that the elongations or the deformation is not the same in all 3 cases. It was delta in the first case, delta in the second case, but 2 delta in the third case. However, if we use this idea of normal strain, okay, that I mentioned a few minutes ago, where we take the total deformation, delta, and divide it by the original length, now everybody can see that we have the same strain or the same description of deformation for all 3 columns. Okay. So this is our formal definition now for deformation that allows us to make comparisons between parts of different size and shape. Okay. So this is what we refer to as a normal strain, and you have a new Greek letter, okay, that you need to become familiar with. Epsilon, lowercase Greek letter epsilon, okay, is equal to delta, which is my deformation, over L, which is the original length. Okay. Some people write this as delta L over L, right? It's a change in length over your original length. But using this delta here, right, it's a little more common. Okay, so this is Greek letter epsilon. Okay, so you're building up quite a collection of Greek letters for yourself, right? And you'll get comfortable with these Greek letters as you go through this course because these are used over and over. Okay, so I had started to talk about starting with 0 force and then keeping and basically increasing that force until we get to these strain values, right? So here's why we would do something like that. What you want to do is you want to plot, okay, basically load versus deformation. So this is what happens if you plot force on the y-axis and your deformation on the x-axis. And again, this is starting from 0 force, right? And then I keep increasing my force, and then I note that the deflection keeps increasing. And what people have found, okay, through a lot of experiments is that up to a certain point, this curve is straight. It's a straight line. Okay? But you can see that these are 3 completely different plots, right? The slopes are all different. So what you do, okay, is, but if you remember, we said that the stress is the same in all 3 cases, right? So if I replace force by stress, okay, and then if I replace strain, which also is the same in all 3 cases, if I replace the deformation by strain, which is also the same in all 3 cases, then you should get 3 identical plots. I'm sorry, having trouble scrolling here, hold on. All right, so here it is, right? If I plot stress on the y-axis and, stress on the y-axis and strain on the x-axis, I get 3 identical plots. And this is what I want, because these are 3 parts for which I'm applying the same stress. These are 3 parts that are made out of the same material. Right? What I want is the same plot that shows me for a given amount of stress I apply, how much strain I'm going to get. So this is a very important discovery in the history of mechanics and materials. People started performing experiments like this, where you start increasing your force from 0 up to some point, and you measure your deformation all along the way. And people always found that for most engineering materials, and we're talking, metals, concrete, certain plastics, wood, for most of these materials, you always get this linear plot when you plot stress on the y-axis and strain on the x-axis. This is what we call a stress-strain plot. And if you get these nice linear plots, it makes it makes the data very nice and easy to work with. So what people have found then, okay, is if you take any material, say steel, okay, or aluminum, then no matter what shape or what size you make your part out of, as long as you keep increasing that force and you keep measuring your deformation, you will always get the exact same stress-strain plot. You will always get this straight line. What that means is that this plot of stress versus strain is a material property. It's a property of the material that you're looking at, that you're performing your tests on. And that's important because this is a very critical material property. Okay, so how do you define a straight line? In fact, this is a straight line that starts at the origin, right? Because at 0 force, I get 0 deformation, or at 0 stress, I get 0 strain. So the nice thing about such a straight line is that you only need one quantity to describe that straight line, or you need one value to represent this material property, right? And as you could probably imagine, that's the slope of the line. So this value of slope is what we refer to as Young's modulus, okay? Or, so let me summarize this. The slope of your stress strain curve is referred to as Young's modulus named after a person, and sometimes it's referred to as the modulus of elasticity. Okay? Here is another symbol for you, and this is not a Greek symbol. Uppercase E is the value that's assigned to Young's modulus. Okay. Now, let me talk a little bit about the alternative term, modulus of elasticity. What does it mean when something is elastic? If you were to look up the term elastic in the dictionary, what would the dictionary say? Well, so elastic or elasticity basically refers to the ability of some object, some material, some person, some entity to recover after something has been done to it. Okay, that's the most general definition of elasticity. Okay, is after you do something to this object, right, it returns to its original state. So in mechanics of materials, elasticity basically means if you apply a stress or apply a force to a part and it deforms, then after you release that force, it returns to its original shape. Okay, and the reason that we use this term for this property is that people from those experiments, right, people found that if you take some piece of steel or aluminum or whatever type of engineering material, and you put a stress on it, and then you let go of that stress, that material does in fact return to its original shape. Under certain conditions. Okay, there are always exceptions, of course, and we'll get into that. Right? So this is modulus of elasticity. And how modulus of elasticity gets used, right, or how it relates to that curve, then you might imagine, right, remember we plotted sigma on the y-axis and epsilon or strain on the x-axis, and you get a straight line, right? So the equation of this line is sigma equals E epsilon, right? We said the slope is Young's modulus, or E, right? This is y equals mx, if you will, right? Equation of a straight line that starts at the origin. This equation is referred to as Hooke's law. Named after a person again. Okay? It is one of the most fundamental equations in mechanics of materials. And most materials obey this law up to a certain extent. Okay? This is a very, very important equation, as I said. And the great thing about it is it's really simple. Right? It's a straight line. And all you really need is the slope of that line, or Young's modulus. So what is... we said that Young's modulus, or this curve, is actually a material property, right? So we talked a little bit about material properties tables last time when we were talking about ultimate stress or ultimate strength, right? The ultimate stress, if you remember, is the stress at which a part breaks. And we said that it was a material property, right? So steel has a certain value of ultimate stress, aluminum has its own value, brass has its own value, and so on. It's the same thing with Young's modulus. So if you go to the materials properties table on the back in the appendix of your textbook, one of those columns is going to be Young's modulus, or modulus of elasticity. Okay. And what are some typical values? If you look in that table, okay, in the SI system, Young's moduli are on the order of gigapascals. They're huge, right? Gigapascal, if you remember, is 10 to the 9th pascals. Okay? And in the US system, we're talking about 10 to the 6 psi. So Young's modulus is usually pretty big, right? At least for the materials that we're going to be concerned about: metals, plastics, woods, concrete. And the reason for that, okay, I mean, just imagine a piece of steel, right? How much does it take to get a piece of steel to deform, let's say, in tension? You need to apply a huge amount of force to even get it to deform by a tiny amount, right? So if you think about it, E is sigma over epsilon. And we have said that you need very large forces to get a very small deformation. So what you have is you get very large sigma values that you're going to divide by very tiny epsilon values, which of course is going to give you a super large Young's modulus. And hence, right, you have values that are in the gigapascals and in the 10 to the 6 psi's. Steel is probably, it's a great material. It's used all over in structures, right? It's used throughout civil engineering for bridges, for buildings, and other types of large structures. And the reason for that is it's very strong. It's got a very high ultimate stress, and it's also got a very high Young's modulus. Let's think a little bit more about what Young's modulus really means. It's a material property, and it's basically a measure of how much something deforms when you apply a certain amount of stress or a certain amount of load to it. So another term that's used, okay, out in the real world at least, it's not a technical term, but out in the real world, a lot of times this is referred to as stiffness. So stiffness, right, is used when we talk about things like a spring. So what does that mean when a spring is stiff? It means you need to apply a very large force to that spring just to get it to deform a little bit, to get it to stretch a little or to compress a little. Okay, so it's the same idea as stress versus strain and as Young's modulus. So that's another way of looking at Young's modulus. Okay, is to look at it as a stiffness. All right, so these are material properties. Okay, and they are available, right, when you look them up in your materials properties tables. In fact, why don't we try and bring one up? Okay, so I'm going to Google. And let me just type in material properties. Yeah, database. Okay, so a lot of times these tables are stored in databases. All right, let's see what we have. So this first one seems pretty good, right? Properties data on over 28,000 materials. So let's click on that. All right, let me see. So, material type. Let's look under material type. Right, and what we want are metals, because metals are the most common engineering materials. All right, so what do we want? We want ferrous metals, let's say. This seems a little too detailed. Actually, this is not a good one because this is if you're looking for a very specific type of alloy. Okay, what I want is a more general type. All right, let's see. How about this one? Materials Properties Database at ResearchGate. No, that's a discussion. Just bear with me here. Okay, I wanted to bring something up that's that will show exactly what's so nice about these properties tables. All right, so let's search. Okay, here we go. We'll just bring up one of these images. Okay. Not a good one. This is a good one, but it's not very clear. Boy, I'm having more trouble than I thought I would here. Okay, here we go. This is a pretty good one. Okay, so this is engineer student, and you can see, okay, this gives you a list of a few different metals essentially, and if you take a look at, let's take a look at just the first one, aluminum, right? What are some typical material properties? Boiling point, okay, definitely, right? All aluminum is going to boil at that exact value, okay? It's going to melt at that exact value. All aluminum has that density, right? That amount of thermal conductivity, and this is the one that we really want, okay? Young's modulus, 70 gigapascals, okay, is the typical Young's modulus for aluminum. Now, obviously, there are different alloys of aluminum, right? And then these properties are going to differ a little bit between the different alloys, right? But this, I would imagine, is pure aluminum, okay? And then you can see for copper, depending on what kind of copper you're looking at, because there's yellow copper, red copper, and actually, no, I'm sorry, that's brass I'm thinking of. But anyway, copper, depending on your source, right, has a Young's modulus between 110 and 128 gigapascals. Okay, chromium, you can see, is much larger, 279. Steel is probably the most important material that you should become familiar with, and it's not here, but steel is usually around 200 gigapascals, okay, for Young's modulus. Now, there's another thing that I should point out here. This is a British website, right? Look at the URL here. There's a .uk. So you notice what system of units all these values are in, right? Everything is in the SI system. So when you look at a US textbook, okay, material properties tables are going to be in both the SI system and the US system. Okay, you can look in your own textbook. Okay, you will find tables in both SI and US. But if you were taking this course in some other country, right, and you look in your textbook, there wouldn't be tables that listed US values. You would only have SI system values. Okay, and just thought that that's something interesting to point out. Okay, so let me close that out. So hopefully you start getting this feel, right, for materials properties tables. They are absolutely critical. Okay, if you go and get a job as a civil engineer, you will rely heavily on materials properties tables, on handbooks, on codes, and things of that sort. All right, so where do these values on these tables come from? You know, someone had to have determined those values. So let me just briefly discuss who came up with those values and how they determined those values. So there are organizations, okay, that basically govern different materials. There's an institute or an organization that just governs steel, one that handles aluminum, and so on and so forth. Now, who funds these organizations? Right? So usually it's the manufacturers. So all the steel producers probably get together and they all fund the Steel Research Institute, or association or whatever. There's all different names, right? Just like all the aluminum producers probably get together and they put in money and they form this group that's going to come up with all the properties for aluminum. And these organizations actually hire engineers that do nothing but test batch after batch after batch of steel or aluminum to come up with these values. And the test that they perform to come up with Young's modulus, okay, looks something like this. This will be very similar to a device that they will use. Okay, this is usually referred to as a materials testing system. And it's very simple in concept. So what happens usually is these systems have one fixed end. Okay, and this example here, the top end is fixed, okay, and the top usually, and it's going to have some kind of a holder. In this particular case, it's going to be a threaded fitting. Okay, so what you do is you machine a piece, okay, as shown on the right here, and you put in this piece, right, you've got threads, and the threads just screw into the fitting on the materials testing system. The bottom of the testing system is an actual platform that's controlled in some way. It could be controlled electrically, right? It could be an electric motor. It could be controlled pneumatically, right, using air pressure, or it could be controlled hydraulically. Now, why all the different methods? Well, for a regular system that you might put on a bench top and that you might use to teach students, you use something that's electrical. You don't need large forces. You're not going to be testing super large parts. Okay, so you don't need large forces, and then usually an electric motor is going to work, right, for pulling on those parts. In civil engineering, sometimes you're testing columns of concrete, and an electrical system simply won't do. Okay, so in such a case, you use a hydraulic system, right? Fluid pressure, right? Oil pressure. You could apply some super large forces using a hydraulic system. All right, but regardless, they all work under the same idea. So this bottom bulkhead, if you will, this bottom platform is controlled, and it can move up and down. All right, it's also got a holder, a fitting, which in this case is also threaded, so your piece also threads into the bottom. Okay. And then what you do is there are all kinds of instruments that are hooked up to this now, especially these days. You hook this up to a computer, the computer takes care of everything for you. But in the old days, right, you obviously had to do more of the manual work, and you had to do some manual data collection. But again, these days, everything is automated for you, right? And in this example, right, when it comes to measuring length and deformation, you would never measure the length of the whole piece, because when you start pulling on a piece like this, it doesn't deform uniformly. Right, so what you do is, and of course, you don't want interference from the threads and from where it's being gripped. So what you do is you mark off in the middle here some length, okay? This is what we refer to as a gauge length. That's the length that you're going to be looking at. You're going to assume that your part is just this little piece here, right, with a length of L. And then when you look at deformation, you just look at the deformation from that original L, okay? You ignore everything above that top red line and everything below that bottom red line. It just make things more accurate, okay? And then the way this works is you start pulling. You start moving that bottom platform down to do a tension test, okay? And you will move it up to do a compression test, right? So you start moving it, and then again, there's a force gauge usually that's attached to this. What it does is it starts measuring the amount of force that's being applied as that piece is pulled. And then there's a machine or some kind of instrument to measure the length. And these days you probably use lasers or something like that. In the old days, people actually stood there and measured, right? With a ruler, or you could have taken, you take pictures and then you make measurements of the pictures, right? So what that means is in the old days, you would actually take a marker and draw 2 red lines on your part, right? And then you kept taking pictures and you kept measuring the distance between those 2 red lines. These days, again, it's very sophisticated. And what you do then is you convert all those length data into strain, right? You basically do delta L over L. And then to get stress, right, you take your force gauge data, those forces, and you divide by the original cross-sectional area. And once you have all that data, then you just plot it. You plot it, and what you're going to find is that there's an initial linear portion, and you just calculate the slope of that line to get Young's modulus. So that's how people determine those values for Young's modulus in the back of the textbook. And of course, these engineers that are hired by these institutes perform hundreds, if not thousands, of these tests. And as they get more and more data, they might update those values a little bit. All right, so just as an aside, at least it was for me, in my junior year, okay, as part of my mechanical engineering lab, we obviously ran a lot of experiments that related to a lot of the courses that we had to take, a lot of our core courses. And one of the most memorable experiments that we had to run was a materials testing lab. And in that experiment, we were given a bunch of different pieces of metal. Okay, so those pieces of metal, and this is another very typical type of materials test. Those pieces of metal were machined into what's called a dog bone shape. These are very flat, very thin pieces. Okay, so these are very thin and flat. And then the ends are kind of flattened and broad so that you could clamp on them. So we use materials testing systems where instead of using screws and threads, we use clamps. So you clamp on the top and the bottom, and then we attach what's called an extensiometer. It's just a fancy length measurement device, okay, clamped in the middle of the part, and then as you pull on this part, it measures the deformation for you. Okay, and so we were given a bunch of these pieces, okay, 3 of each material. We were given several different materials, 3 of each of those materials, just so you could do more than one test for each material. And then what we were supposed to do is we were supposed to mount all these pieces that we were given to a materials testing system, as I just described. And then we were supposed to collect all that data. We pulled on these pieces until they broke. Okay. And then we converted our data to stresses and strains. We plotted out stress versus strain. And then we took the slope of that straight line portion and found the Young's modulus for all these different materials. Okay? And then based on the Young's modulus, and of course we calculated the ultimate stress, based on the Young's modulus and the ultimate stress, we were supposed to determine which material each of the pieces we were given was. Okay? And that was a very fun, very informative experiment because it actually allows you to see exactly how Young's modulus is determined and ultimate stress, and it's quite a learning experience to actually perform the test. Okay, and usually the values that you get come very close to the values in the materials properties tables. All right, so what we did was we took for each piece, for each part, right, we had 3 separate values of Young's modulus. We averaged the 3 values, and then we took that average value, went to the materials properties table, and compared it, right, and tried to find exactly which material that corresponded to. All right, so those of you that continue on in mechanical engineering or civil engineering, you might have a very similar lab in your junior year, right, once you transfer to a university. All right. So let's continue on with our discussion. Now, what does a typical plot look like? As I said, in the experiment that I performed, we pulled the parts until they broke, right? And that's usually what these scientists would do, the ones who are responsible for coming out with the values in the materials properties table. So these are typical plots, okay? There are two different types of materials. In the left is some alloy of steel. On the right is an alloy of aluminum. They are somewhat similar, and then they have some distinct features that make them different from each other. Okay, so we'll talk a little bit about each. These are very typical of metals. Okay, most metals actually will look either like the plot on the left or the one on the right. How about something that's not metallic? Something that's brittle. Okay, maybe a ceramic or a piece of chalk, right, or concrete. If you pull it in tension, its stress-strain curve, okay, looks something like this. Okay, very different from the other two that you saw, right? So what we're going to do is we're going to start talking a little bit about the one for steel. Okay, so this is that plot for steel just blown up a little bit. And I want to start talking about what exactly is going on. All right, so at the origin, right, keep in mind that's where we start our test. That's at 0 force or 0 stress and 0 deformation or 0 strain. What happens then is as you start pulling, right, initially it's very hard to deform a piece of metal, especially something like steel. So you have a very steep slope, okay? And this is linear. This is what we were talking about. This linear portion here, right, this is initial portion, is if you go back a few slides, okay, it's this. It's these plots. Okay? So that initial portion is the linear portion, and Young's modulus comes about from taking the slope of that line. Now, in something like steel, okay, this straight line goes up to a certain point, and then what happens is it peaks and then dips, as I've kind of blown up here. Okay, I blew it up even further here. It peaks, then dips, and then it starts going back up again. Okay, it peaks, dips, starts going back up again, and now it keeps going up. It's not linear. It keeps going up until it reaches a peak, then it goes down a little bit again, and then it breaks. So, let's go into detail here. Okay, that linear portion is usually referred to as the linear elastic region. It's linear, right? And it's elastic, meaning that at any point in this linear portion, if you let go of the force you're applying, your material just follows the slope, this line, back to the origin. It goes back to its original shape. Okay? So that's the linear elastic region. Linear elastic region, okay? And the important property in the linear elastic region is Young's modulus. Now, what happens if you go past the linear elastic region? Your plot kind of goes up and reaches a peak, okay, and then it dips. Now, this region here is what we call yielding. So yielding happens in something like steel. Okay, steel yields. And what we mean by yielding, okay, usually is it's kind of the point of no return, if you will. And what I mean by that is if you stress something all the way to the yielding region, okay, then your part is no longer elastic. Meaning if you let go of the stress at that point, then your part will not return to its original shape. Okay, you have caused some permanent deformation in the part. The point where yielding begins, or the stress at where yielding begins, is what we call the yield point. And the yield point, theoretically, is where the linear portion ends, right? But that's very hard to determine. I mean, if you blow up that region again, right, and you start looking, what happens is you have this linear region, you have this straight line, and then it starts to get more and more, it starts to deviate more and more from that straight line, okay? Eventually it reaches that peak, then it goes and it dips, and it's very difficult to determine where exactly the straight line ends. So what people have found works really well is you just go to where that valley is, right? After it's peaked and it goes back down, if you look at the very bottom of that dip and you just draw a straight line across, that usually is dead on as far as where the linear portion ends, okay? So that point, both of those points actually, right? This is what we call, the stress corresponding to that is what we call the yield stress. So the yield stress is also a very important quantity, right? What does it really denote? The yield stress is the largest stress you could apply to your part without it becoming permanently deformed. If you apply a stress greater than the yield stress, your part will deform permanently. Now, how much it deforms depends on how much you stretch it past the yield stress point. Okay, so that's very important. Okay, and then all the way up to where the concave up portion of this curve ends is what we call the yield region, right? And in the yield region, basically, if you look at that, okay, the yield region is it's actually very interesting. If you try to think in terms of stress versus strain, okay, within that yield region, you can see that the slopes are very small. Okay, you almost have like a horizontal line there, right? And what that means is you had kept increasing the stress to get very little strain, to get very little deformation all through the linear portion, right? Once you hit the yield point, what that essentially means is you actually can decrease your stress a little bit, or you could keep your stress at the same amount, and that part just stretches. It deforms quite a bit, right? Even though you're not increasing the stress. Okay, so you basically apply a stress all the way up to the yield stress, and then you just hold it at that yield stress, and the part just stretches at that stress level. Okay. Now, where that concavity changes, right, so that the curve becomes more concave down, okay, that becomes now what we call a strain hardening region. And what that really means, okay, what the strain hardening region means is, again, in terms of stress strain, you can see that the slope starts to increase again. So, essentially, you now have to keep pulling harder and harder to get it to stretch more. Okay, and in fact, you can see, right, for a large portion of the curve here, you do have to increase your stress significantly to get the part to stretch. Okay, so this region is referred to as a strain hardening region. And this goes all the way up to the peak, right on top here. Now, the peak then, right, is going to be the largest stress value that you're going to find on this curve. So this is what we call the ultimate stress. Okay. So last week, you might have gotten the impression that the ultimate stress or the ultimate strength is the strength at which your part breaks, right? And I probably gave you that idea. But in fact, okay, in engineering, it's not necessarily the point where your part breaks. It's just the largest stress that you could apply to your part before it breaks, okay? But not at the point at which it breaks. And I'll get more into that in a few minutes, all right? So after the ultimate stress, what you can see is that this curve actually dips again. It actually goes down, right? And again, I'll talk more about that in a minute, right? And then finally, if you keep applying a stress, eventually that part breaks, okay? And then the point at which it breaks is what we refer to as the rupture stress or the breaking stress, sigma sub b, okay? So those are the important stress values, the important values that you need to be aware of, okay? So let's list them. You need Young's modulus, okay? So from your stress strain curve for steel, you need Young's modulus. You need sigma sub y, that's your yield stress. Then you need your sigma sub u, that's your ultimate stress. Then sigma sub b for your breaking stress or your rupture stress. Okay? These are the 4 critical values that you need out of the stress strain curve for steel. Let's look at the one for aluminum for a second. The one for aluminum is actually quite similar. Okay? The only thing that's missing compared to the one for steel is that there's no yield. There's no yielding region, right? In steel, we had gone up, then dipped, and then continued, right? There's none of that going on here. Right, there's no peak and then a dip in aluminum. And what that really means, okay, there's only one major or one critical consequence of that. And it's that it's very difficult to determine the yield point for aluminum. Okay, because for aluminum, I mean, again, the yield point really is the point where the line ends, the line stops being linear, but that's very hard to determine sometimes. And a lot of times it's kind of subjective, right? Especially if you don't have a perfectly straight line, which you never do in experimental data. So how do you determine the yield point in aluminum? Because other than that, right, everything else is the same. I still have this peak here, right, that gives me, that results in the ultimate stress, and then there's still the rupture stress, right? So the way we determine the yield point for aluminum is through what we refer to as the 0.2% offset method, okay? And before I talk about that, right, let's go in detail about units for strain. So we talked about units of stress last time, right? It had units of pressure. But for units of strain, if you remember, strain is delta over L. What's delta? It's a deformation or a change in length, right? It's a delta L over L. So what that means is in the SI system, this is going to be something like meters per meter. In the US system, it might be inch per inch, right? It might be foot per foot. Doesn't matter. You see what's going on here, right? You get something that's dimensionless. It has no units, okay? So strain by itself has no units. But we also said that strains are usually very small for the metals and the other materials we're going to look at, right? I could apply a very, very large stress to steel, and I might get less than a millimeter of deflection, right? I might start off with a 1 meter long piece of steel. I apply a very large stress to it, And it might deflect only a small fraction of a millimeter. Okay, so how large is the strain in that case? It's going to be tiny, right? So what some people do, okay, is they actually express strain as a percentage. So strain really is a fraction if you think about it, right? It's how much deformation you have divided by the actual length. So it's a fraction, right? If I have something that deforms 1 millimeter, right, which is 0.001 meter, and its original length was 1 meter, then my strain is 0.001, right, as a proportion or as a fraction. Now, that's tiny. That's pretty tiny, right? So what a lot of people do is they express this as a percentage. So, of course, you multiply by 100, or you move that decimal place to the right by 2 places, and you get 0.1%. Okay? So this is another way of expressing strain, is as a percentage. So now let me go back to what we were talking about as far as determining the yield point or the yield stress for aluminum. In aluminum, we use what is referred to as the 0.2% offset method. Okay, so 0.2% means we are looking at 0.2% strain, which in terms of an actual strain or an actual fraction is 0.002, right, as shown on this plot here. So what this method refers to is this. It says you go to where the strain is 0.002, and then what you do is you draw a line that's parallel to the linear portion, or at least, like some portion of that linear portion. So you try and draw something that's parallel, and then where this new line that you draw intersects your stress-strain curve, right, you just go across and read off that stress value, and you're going to take that as your yield stress. So people have found that this is a pretty good approximation of where the linear portion ends, right? And that's just kind of the accepted method that's used. There might be better ways, but this is historically the way that's used. All right, so that's the stress-strain plot for aluminum. All right, it's very similar to the one for steel. Now, what I want to talk about next is just quickly why aluminum and steel have this ultimate stress that's actually not the point of where the part breaks, right? Why is there this peak? Why is there this peak in these stress-strain plots? And the reason for that is basically the way that mechanical engineers come up with these stress-strain plots. So in mechanical engineering, or pretty much in a lot of engineering, we like to do things in a way that's as efficient as possible. What that means is we will sacrifice a little bit of accuracy if we could speed things up by some significant amount, right? If I could sacrifice maybe 1% accuracy and be able to gain 10% efficiency, or be able to do something 10% faster, then I am willing to make that sacrifice, right? That's engineering. Engineers are very practical, right? As far as we're concerned, I mean, what's 1% accuracy, right? I'm willing to ignore 1%. So what we do when we create our stress-strain plots, right, is we use our sort of this definition of strain that we came up with, where we always take the deformation and divide by the original length. L here refers to the original length. All right. which is good, which is fine. But for stress, we take the force and divide also by the original area. These are all original values. Original meaning undeformed. Okay? Now, that's going to be a problem when it comes to stress. Because what happens as you keep pulling on the part as it stretches? What you know is that the area is going to keep decreasing, right? When you keep pulling on something and it stretches, then it becomes thinner and thinner. Right? In fact, in something like steel, you end up with what's called a necking. So this is a picture that shows a piece of steel, right before it broke during the tension test, and then after it breaks during the tension test. You can see that it forms what's called a neck, which is this region in the middle that just really, really thins out. Okay, and then ultimately that's where the piece of steel is going to break. And if you look at the cross section, right, of where it breaks, it is much smaller than the original cross section. So when you make use of the original cross-sectional area to calculate your stresses, it's actually not taking into account the deformation that's happening to the area. And we're willing to forget about that, okay? Because that only really comes into the picture when it starts to deform quite a bit. And if you look at our plot, right? If you look at the plot for steel, where does it really start to deform? It really starts to deform, kind of starting at the yield region, but definitely in the strain hardening region. And, as far as engineers are concerned, we don't care too much about what goes on in the yield, the strain hardening, and the necking regions. And why is that? Well, remember, once you get past the yield point, your material is permanently deformed. Okay? That's not something that we really want to happen. So in most engineering applications, right, if you're designing a bridge or a building, you want to keep your materials, keep your structures in the linear region. You don't want to load that part into the yield region or into the strain hardening region. So in the linear region, how much deformation is actually happening? Look how steep that curve is in the linear region, right? It means you have to apply very large stresses just to get a tiny amount of strain. So there are very little strains. There's very little deformation. And if there's very little deformation, what can you say about the change in the cross-sectional area? It's almost nothing. Okay? So in the linear region, we really don't have to worry about the change in the area. It's only once you get into the yield and the strain hardening regions where the change in the area has an effect. So we don't care too much about that, right? We know that if we use the original area, that we're losing some accuracy, but it's not too critical. Now, physicists are completely different, right? Physicists are very precise. They always want to know exactly what's going on. Their whole goal is to understand exactly what's happening. So when a physicist does a materials test and comes up with a stress-strain plot, they make sure that their stress is force divided by the current area. They don't divide by the original area. They keep monitoring the change in the area, and as the area changes, right, that's what they divide their force by. And that gives you what's called a true stress. Okay? The definition we use is referred to as an engineering stress. And physicists don't use the engineering stress. They think it's completely incorrect. It's not accurate. Right? And engineers say, so what? But, okay, if you were to take a look at the stress-strain curves for using engineering stress and using the true stress, here's what you would find. I'm going to draw our engineering stress-strain plot for steel, right? That's what we talked about just now. Let me change the color here. When a physicist creates a stress-strain plot for steel, they pretty much get the exact same curve, okay, in the linear region. And then there's, it might deviate a little bit in the yield, but it's pretty much just still the same curve. And then what happens is their curve goes like this. Okay? So what's the takeaway point? For a physicist, sigma ultimate is sigma rupture. Okay? The largest stress is also the stress at which the part breaks. For us, sigma ultimate is before sigma break. Okay? So that's why we get this peak in our curve, and then it dips down to the breaking point. It's because we use the original area instead of the current area. Okay. All right. So that's the explanation for that. All right. For those of you that were wondering why that would even happen. Okay. So let's just go back to the plot for the brittle material, right, and just talk about that really quickly. In the brittle material, okay, you basically have almost all of the linear portion. Then you get this region that just deviates a little bit from the linear portion, and then the part just breaks. So what that means is there's no yielding, there's no strain hardening, there's none of that. Okay, there's very little deformation. Right? It means you have this linear portion. You go a little bit past the linear portion and it just breaks. And in a brittle material, what that means is there's almost no permanent deformation. Okay, this is a piece of a brittle material. This is probably some kind of a ceramic or something that's broken after doing a tension test. If you put these two pieces back together and measure that length, it will barely be longer than the original length. On the piece of steel that we showed earlier, okay, if you took the two broken pieces and placed them back together and measured that length, it would be significantly longer than the original length, okay, because of all the permanent deformation that had happened. All right. So let's talk a little bit more about permanent deformation. And a lot of this is comes about because of experimentation. Okay? People have determined a lot of these phenomenon because they performed a bunch of experiments. So let's use steel again, since it's one of the most important engineering materials. What people have found, okay, as far as permanent deformation, right, is this. The way you're going to determine if you stretch your part past the yield point. So there's my yield point, right? This is sigma yield. What people have found is that if you stretch your part past the yield point, right, and you get permanent deformation, the way you determine the amount of permanent deformation is this. Let's say I stretch my piece of steel all the way to this point on the curve. Okay? So I've gone all the way here. What happens when I let go of my stress, okay, is that my piece will try and recover, right? And it'll recover almost to its original shape, but not completely. And how much permanent deformation it has, okay, I could determine by simply drawing from this point where I release my load, right? I draw a line that's parallel to the linear portion. And where this line crosses the strain axis or the x-axis, the amount of strain there is the amount of permanent deformation that I have. So let's say the strain is 0.001, right? What that means is the amount of deformation that I have is 0.1%. Okay? So if my piece was originally 1 meter, right, then 0.1% of 1 meter is 0.001 meter. That means my part is now 1.001 meters long after I release the stress. All right, and then here's the interesting thing. The next time I load this part, now it just follows this new curve, okay, up there. And then once it gets to that point, it follows that original curve. Okay? So that's something interesting that happens. Okay? But that's how you determine the amount of permanent deformation that you have once you stretch it past the yield point. All right, so let's move on then. Okay, so we talked about all this. A little brief discussion about compression. A lot of metals actually have the same Young's modulus in tension and compression, and some of them even have the same ultimate stress in tension and compression. Now, that's not to say all of them are like that. There are metals that behave differently in tension and compression. So if you look at your materials properties table, okay, for things like ultimate stress, okay, you will see 2 columns of values. One is for tension, one is for compression. Okay. In cases where only the tensile value is listed, you could basically assume that the compressive value is the same. If the 2 values are different, then you will see 2 values listed. Okay, so that's all I need to say about that. Hooke's law we already talked about, right? One of the most important laws in mechanics of materials. So Hooke's law, now you can say, basically applies to the linear region of your stress-strain curve. And the linear region, of course, is the region that we're going to operate in for most engineering applications. So Hooke's law is one of our most important laws because it kind of defines the region that we're working in. Okay, the next thing, the region past the yield point is sometimes referred to as the plastic region. Okay? Just so you're used to this term. Now, the textbook in this chapter actually devotes a section to talking about the plastic region and the theory and approximations that you could use there. We're not going to get into that, okay? Since in mechanics and materials, right, especially at this introductory level, we're only interested in the linear region. So I'm going to skip over all that talk about the plastic region. If you were to continue on in graduate school for mechanical engineering, you actually can take a class in plastic behavior. All right, so this I talked about. Okay, the next thing we're going to talk about is something that's referred to as fatigue. Okay. So there's some historical context to this, right? And it comes from observation. So people, after people determined what yield stresses were, what ultimate stresses were, they thought that those were values that kind of give you guidance, right, on how much you can load a part. And that was fine and good, except in cases where a part was repeatedly loaded and unloaded. So you're talking about something that's cyclically loaded. It could be like it could be a shaft, right? It could be something like an impact drill. When you use an impact drill, it's hammering that drill bit, right, at a very high frequency. And if you keep hammering and hammering, right, you could sort of try and calculate the stress that's being applied every time one of those hammering forces is applied, right? And you might think that as long as that stress is less than the yield stress and definitely less than the ultimate stress, then it's fine. You could use this drill bit forever without it breaking. But what people found is that after a certain number of cycles, actually, right, pieces did break. Things did start to break. Okay, so this is what's referred to as fatigue. Fatigue is basically when you load a part over and over. And every time you load it at a stress that's well below the ultimate stress value. Okay? But eventually this part still fails. Now, the reason for this, is something that's microscopic in nature, right? Every time you load and unload, you're probably doing some kind of micro damage to the part, so that eventually, it gets weaker and weaker. You're decreasing actually its ultimate stress and eventually you decrease it to a value that's so low that even a small amount of stress will break it. Okay, so unfortunately, there's no theory behind this. Okay, and there's no way of predicting how many times you can load something before it breaks. So what people have done, again, is perform a bunch of experiments, and then they came up with what are called SN diagrams. That's a stress, right? S for stress. N stands for the number of loading cycles. So the way these these curves, right, are produced is fairly simple. So you could set up some kind of an automated system, right? You basically have a machine that's going to load and unload your part. And then there's just a counter attached to this machine, right? Every time it loads and unloads, it increases the count by 1. And of course, you have to set the stress value, the stress level that you're going to load your part at. Okay? And then you just let this machine run. It loads and unloads, right? It keeps going, it keeps counting how many times it does this until your piece breaks. Okay? And then you note down the stress level that you applied and how many cycles you applied before it broke. Then what you do is you choose another stress level, right? You take another part, you choose another stress level, and you perform the same experiment. So eventually, you come up with a bunch of data points, okay? So you might have a data point here, a data point here, a data point here, right? And then you just fit a curve through all your data. And this curve will let you predict, right, for a given stress cycle, how many times you can load and unload your part. And what you find, right, is these curves will eventually flatten out. As you decrease the stress level, they all eventually flatten out, okay? And what that means is there actually is a stress level below which you can load your part forever, at least theoretically. Okay. So this, again, is fatigue. And if you're working on a project where you do have fatigue loading, right, where you're designing a part that's going to be loaded maybe millions of cycles, then there are more detailed handbooks that contain more that contain much better graphs than this. Okay, so what this is supposed to do is to show you how you would use the plots that are in those handbooks. So you're aware of this phenomenon, right, and what you do if you encounter something like this. Okay, so let me move on. Deformation under axial loads. Okay, so keep in mind, we're going to go back to tension compression because this is the first type of load that we've been looking at. It's the simplest type of load, right? It's when you have a long structure and you just pull on it until it stretches, or you compress it until it gets shorter. Right? So this is what we call axial loading. Axial loading, again, is just tension compression. The reason that it's called axial, right, is that if you have a long part, then the long axis just runs along the center of that part, right? And then if you load along that axis, then that's an axial load. All right, so why are we going back to actual deformation? I thought we decided that we're going to stick with this idea of a strain, right? Well, strain is good when you make comparisons between different parts, but there are still going to be situations when you're working on a problem and you want to know you want to be able to predict what the actual deformation is. Okay, how much is your part going to stretch, right, when you apply a certain amount of stress to it? So here's how we're going to derive this equation. You can see that the equation is delta, or the amount of stretch, or your deformation, is equal to P. P is the axial load, or your axial force. L is the length. A is the cross-sectional area. And now E is Young's modulus. So what I want you to think of is this, right? Think about what deformation is actually dependent on. Deformation in this case, right, is a function of load, length, area, and material. Young's modulus is a property of the material. Okay? So that's what your deformation is dependent on. And we'll come back to this in later chapters, because there are going to be analogies even when you apply different types, when you apply other types of loads. Okay? All right, so where does this equation come from? Delta is equal to PL over AE. So this is a very critical equation that you'll probably memorize, because you're going to be using it over and over. But where it comes from, okay, is very simple. We have two definitions, right? Sigma. We've got sigma is P over A. We've got epsilon now is delta over L. But now we know that sigma and epsilon are related by Hooke's law. So sigma is equal to E epsilon, right? And now I just substitute. Sigma is P over A equals E times delta over L. Okay, and solve for delta. You get delta is PL over AE. Okay, it's literally that simple. So in fact, you don't even need to memorize this equation, right? If you ever forget this equation, let's say you're working on something and you don't have your textbook handy, you don't have a computer handy, right? And you need to come up with this equation. Well, here's how you derive it, okay? Real simple. So anyway, right, once you have this equation, okay, you can now use this to predict how much a piece is going to deform when you apply a force to it. So you've got this structure, right? This column, if you will, or this rod that hangs down from the ceiling. You know its length, you know its area, and basically you're going to ask yourself, if I apply this certain amount of force to it, how much is it going to deform? Well, now you have this equation that will allow you to predict and to answer that question. So when you have a single rod like this, then it's very simple, right? You just plug in all your values. Or there's another way to look at this, right? If you remember, we talked about design problems last time. I had said that in mechanics of materials, a lot of the problems you encounter are analysis problems where you simply plug in values and you solve for your deformations and your stresses, right? And now, of course, your strains. However, there's also a good amount of problems that are design problems. Okay, so a design problem might be something like, design me a column, design me a rod, right, where I'm going to be applying 500 pounds to the end, and I want it to have a radius of 1 inch. I'm going to make it out of steel, right? And I don't want it to deform by more than 0.001 inch. Okay, find me the length. Okay, so that might be a design problem. Another variation is, I've got a 1 foot long steel rod for which I'm going to apply 500 pounds. I don't want it to deform more than 0.001 inch, right? How large should I make the diameter? Or what's the smallest I can make the diameter? Okay. So you could kind of imagine. I mean, think of all the things you could be asked to solve for, right? In the analysis problem, you're being asked to solve for delta, but you could also be given delta and be asked to solve for P, right? You could be asked to solve for L, you could be asked to solve for A, and finally you might be asked to solve for E. Okay, so those will be design problems. If you were asked to find P, L, A, or E, that would be a design problem. If you're being asked to find delta, that's a simple analysis problem. All right, so that's what happens if you had a single rod. Where this becomes a little more difficult, okay, is if you have multiple rods. So let's take a look at that. So let's say I've got rods now that are, I might have something like this. Okay, it's 3 rods that are maybe welded together. They could be 3 different materials, right? And I apply a force at the end. A force P. Okay. And now I want to know, what is the total deflection, right? And this is what we call a composite rod. A composite rod is a rod that's made up of either different materials, right, different segments, and so on. All right, so how do you treat something like this? Well, it's very simple, right? What you can imagine is, if you pull on this free end, then let's call this rod 1, rod 2, and rod 3. Rod 1 might stretch by some amount, 2 is going to stretch by some amount, and 3 is going to stretch by some amount, right? So you could say that delta, that's the overall deflection, is equal to the deflection in 1 plus the deflection in 2 plus the deflection in 3. And what that means is PL, the length of 1, over area of 1, E of 1, right? It could be 3 different materials, plus, let me put this piece of 1, plus the force in 2, length of 2, A of 2, E of 2, plus P of 3, L of 3, A of 3, E of 3. Okay? So the idea here is very simple, right? And in this problem, okay, all you need to be told is the length of each of these pieces, right? Maybe the diameter of each of these 3 pieces, and then the material that each of these 3 pieces is made out of. Okay? And probably everybody is going to look at this and say that the force in 1, 2, and 3 are all equal to P. Okay? Whatever value that is. It could be 20 kilonewtons. It could be 1,000 pounds, right? Whatever the case might be. All right? And that's fine. But formally, okay, how do I find P1, P2, and P3? This is mechanics of materials. right? Obviously. And I have mentioned in your very first lecture, right, our previous lecture, that when you calculate stresses, your stresses are force per unit area, but that force that you're referring to is the internal force acting on your part. Okay? We never, ever use external forces to determine stresses. So in this problem, okay, when you say that P1 and P2 and P3 are all the same, and that they're all equal to P, that's fine. But if you just assume that and just kind of looked at this as if P1, P2, and P3 are all external, right? They're all equal to that external force P, then that would actually be incorrect. P1 and P2 and P3 are the internal forces in each of rods 1, 2, and 3. In this particular problem, this is so simple, those internal forces do happen to be equal to the external force P. Okay? But it's not always going to be like that. All right. So let me talk a little bit more about this idea of internal forces. All right. So let's add a page here. All right, so in that particular problem, okay, you had 3 rods. And we had, let me put in numbers, okay? Maybe some people I know prefer to work with numbers rather than these symbols. So let's say this is 1 kip, 1,000 pounds, okay? And we had a fixed support here on this end. This is now where we're going to get into this idea that every single mechanics of materials problem is first and foremost a statics problem. Okay? This is a static equilibrium problem first. And what that means is, okay, in a problem like this, you find your reaction first. So I have a fixed support on the left. If you think back to statics, this is actually a 2D problem. Okay. In fact, it's more or less a 1D problem. If you look at this, you just have forces in the x direction or in the long horizontal direction. So even though a fixed support can have 3 reactions in 2D or 6 reactions in 3D, in this case, what's the only reaction of your support? It's a force in the horizontal direction, right? So basically, you're going to say that there's some unknown reaction here, okay? This is going to be very simple, but I just want to go through the whole process because this is a process you're going to apply when the problems get harder, okay? And you're going to say sum of forces in the x direction is equal to 0. Right, so this is my reaction x, let's call that, right? And this is equal to 1 kip. And I assume my reaction is in the negative x direction, right? So I just put minus r sub x, and I solve for r sub x, right? R sub x is equal to 1 kip. Now, a quick word about signs and directions here. When I have a simple problem like this, and I know my reaction is going left, right? I just assume it's going left. So notice I put in the negative sign because I already know the direction. And when I solve for my answer, it's positive. So every time you solve an algebraic problem like this, and your answer is positive, what does that mean? It means you assumed correctly. Okay, so Rx, I had assumed was going left. I get an answer that's positive, so I was right. Rx is going left. Another way of solving these problems is to always assume that your unknowns are positive. So I'm going to say And what that meant is, since I don't, if you look at this and just say, well, I don't care what direction Rx is, I'm not even going to try and determine that. I just assume it's positive, right? And you could always do this. You could always assume that your unknowns are positive, okay? And now you solve for it. What is the value of Rx here? It's negative, okay? And then what does that mean? It means you assumed incorrectly. You had assumed Rx was going right, and it's actually going left. Okay? So there's Rx going left. It's one kip going left. All right? So this is the statics part of the problem. Okay? You find your reaction. Now, obviously, it's not always going to be this easy. This is the absolute simplest case that you're going to find. All right? So now that I know my reaction, I need to now find the internal force in every single one of these segments, 1, 2, and 3. So how do I do that? If I look at segment 1, okay, I know that in segment 1, I've got this force now, that's one kip pulling towards the left, right? And segment 1 must be in equilibrium. One of the most important concepts in statics is that if you have a structure that's in equilibrium, then every single component of that structure must be in equilibrium. Every little piece that you look at in that structure must be in equilibrium. Okay? So if this whole structure, if this composite structure is in equilibrium, then 1 by itself must be in equilibrium, 2 must be in equilibrium, and 3 must be in equilibrium. All right? So how do I keep 1 in equilibrium if it's got this one kip force pulling on the left? Well, I must have one kip pulling on the right. Okay? Does it matter which part of 1 I look at? Like, what if I just took this piece of rod 1? That means I don't even look at the whole piece. I just look at half of it. Right? What is the force now at this, right in the middle here? It's still one kip. Okay? So you could see, it doesn't matter where I look at segment 1, the force on it, on the right-hand side, is always one kip. Okay? So what that means is the internal force in segment 1 is always one kip. Okay? And that's important. This is how you're going to determine internal forces in different segments. So what I refer to this as is you make a cut. Okay? You make a cut in the middle of your segment. Just make a cut somewhere. Right? And it doesn't matter where you make the cut. If you determine correctly where your segment is or what constitutes your segment, then it doesn't matter where you make that cut. The force at that cut will always be this one kip. Okay? And then that's the internal force. All right. How do I determine the internal force in rod 2? Okay, let me erase all of this. Well, so in rod 2, okay, that means I could cut out any piece of rod 2, and then it must be in equilibrium. And the force at the cut is going to be the internal force that's in 2. Well, here's a problem. If I try to just look at 2 by itself, I know it's in equilibrium, right? But do I know what the force is acting on the left-hand side and what the force is acting on the right-hand side? I do not. So you would never look at 2 in this way. What's the better way, or what is the only way really to look at segment 2? You need some kind of anchor. And what I mean by an anchor is you actually need to use one end of this whole structure. So a lot of times people will use the left-hand side as their anchor or as their reference. Okay, so what that means is I have to include all of segment 1, then I include 2, and I don't need all of 2 now. I'm going to make a cut, make an arbitrary cut. Okay, so I just go somewhere here, and the reason I include 1 is that 1 has this external force on it. Okay, I need one of my external forces in order to make a determination on the internal force. Remember, I had said that external forces are not your internal forces, but I do need external forces to determine what my internal forces are, right? My internal forces are dependent on my external forces. So what is going to be the force at this cut on part 2? Well, I know this whole piece must be in equilibrium, right? The whole structure is in equilibrium. If I cut out this part of it that includes 1 and half of 2, then this must be in equilibrium as well. So the force in 2 must be 1 kip. Okay? And then you could do the same thing for 3, right? Make a cut somewhere in 3. You have to include this whole thing. And the internal force in 3 now is also going to be 1 kip. All right? So this is very important. Right? How you determine internal forces in your segment is going to be very important. So now let me give you a more complicated example. So I still have these 3 pieces. 1, 2, and 3. I'm still going to fix, all right, this end. That's fixed. I'm still going to apply 1 kip at the end here. But now, let's say I'm going to push on there with 1 kip and 1 kip. So the reason I'm putting these forces in 2 places is just so I don't get a moment, right? We're not dealing with bending here. We're trying to compress or pull on these parts. Okay, so I apply these 2 forces so they balance out, right? Just so I don't bend this in one direction or the other. And then in the middle of this part, in the middle here now, I'm going to apply, let's say, three kips. Okay. And now I still want to find what the total deformation is on this piece, on this composite piece. Okay, so keep in mind, right, we had already determined that in order to find the total deformation, I just add up the deformation in each piece. So that means delta total, let me put that, delta total is the sum of your individual PLs over AEs. In the previous example that we did, right, we had 3 segments, we had just the 1 kip pulling on the right. How many summation terms were there? It was 3. How many in this case? I want you to think hard about this. How many segments are you going to have if you try to sum up all the PL over AE terms in this problem? And it's not 3. It's not 3. Okay? Anybody have an answer? If you think it's 4, okay, then you are correct. There are 4 segments here. And why are there 4 and not 3? So it has to do with this 3 kip force that's being applied, okay, on the left. So when you look at that, okay, remember I had talked about making a cut, right? You make a cut anywhere within a segment to determine the internal force. Well, if you look at this portion here, what happens if you make a cut on this left piece, on this largest piece? If you make a cut to the left of the 3 kip force, is the internal force there going to be the same as if you made a cut to the right of that 3 kip force? No, right? You would get 2 totally different internal forces. So this first piece here, this very first piece, is actually, right, this piece, you can't treat that as one segment. You have to treat it as two segments. Okay? So here's another way of looking at it. If you look at this in each term of this summation, it's PL over AE. What that means is anytime a P value changes, an internal force changes, you should have a new segment, right? And then anytime your area changes, you should have a new segment. Anytime your E or your Young's modulus value changes, you should have a new segment. Okay? So remember, change in internal force, change in area, or change in material. Okay? Anytime you have one of those three changes, you have a new segment. And L, of course, is the length of each of those segments. Okay? So let me kind of give you a good way of determining how many segments you have. Okay. You use a reference. Again, most people will choose the left-hand side as their reference, and then you just start moving towards the right. Okay? So I'm going to start here. I start moving towards the right. Once I encounter an external force or an applied force, I know that that force will split this into two segments. Okay? So once I start here, once I get here to the force, I know that's one segment, and I keep moving. Once I get here, that's going to be a change in area and maybe a change in material, right? So that's a new segment. I now have two segments. I keep moving, nothing changes until here. That's a change in everything, right? You see these one kip forces being applied there. So that's a change in internal force. That's also a change in area, and it's a change in material. So I've got a change in all three. So this is one segment. That's my third segment. And then, of course, I keep moving until I get to the very end, and that's my fourth segment. Okay? So in this problem, there are actually 4 PL over AE terms. And I would have to give you the length of each of these segments. I would have to give you the diameter of each of those segments. Right? I would have to give you the material or Young's modulus for each of those segments. But I wouldn't have to give you the internal forces in each of those three segments. You have to determine that for yourself. Okay, so let's go ahead and determine the internal forces in our segments. So what I want you to do is this. You're going to specify each of your segments, right? So I'm just going to do this. Okay, this is segment 1, this is segment 2, this is segment 3, that's segment 4. And our next step is to find the internal force in every one of these segments. So here's what you're going to do. Remember, this is first and foremost a statics problem. So I have to find a reaction at the left-hand side. So sum of forces is equal to 0, right? I've got 1 kip going towards the right, 3 kips going towards the right, that's 4 going towards the right, and then I have these 2 kips going towards the left. What do I need to have equilibrium? I need 2 more kips going to the left. Okay, that's my reaction. Everybody see that? If you don't see that, go back and review your statics. So 2 kips going towards the left. All right. And now I'm going to start making cuts in the middle of each one of my segments. So for the first segment, I have this. I make a cut in between. I've got 2 kips. That means I need 2 kips going towards the right. Okay? So the internal force in segment 1, so P1, is 2 kips. Now, I need to specify whether that's positive or negative. Remember from last time, positive, it means tension, negative means compression. It should be pretty obvious to you what this is, right? This is positive because segment 1 is in tension. Another way of looking at this is, remember that the left-hand side is your reference, right? So this is your reference, and then that 2 kips at the cut is pulling towards the right. You always look at your reference as being fixed. So if the left-hand side is fixed, and I'm pulling with 2 kips at the right, going towards the right, then that 2 kips is trying to elongate this segment, right? So P1 is 2 kips in tension. How about P2? I'm going to keep my reference. Okay? I'm going to keep my reference. And what that means is I now make a cut within segment 2. That means this 3 kips has to be included. There's 3 kips there. Okay? What do I need now at the cut for equilibrium? I need 1 kip going towards the left. And now, again, the left-hand side is your reference, so it's fixed. 1 kip pushing towards the left at the cut means P2 is compression. That's negative 1 kip. All right, let's move on. In the 3rd segment, if I make a cut in the 3rd segment, I make a cut in the middle, right? Nothing really changes between the 2nd and the 3rd cuts, right? That means I still need 1 kip. 1 kip compression. So P3 is also a negative 1 kip. Okay. And finally, my 4th piece. So if I make a cut in segment 4, it means I have to account for these 2 1 kip forces. 1 kip, 1 kip. Okay. And then segment 4, I make a cut there. So what do I have now? I have 2 kips starting from the left. 2 kips going left, 3 kips going right, and then 2 more kips going left. Right? It means I need 1 kip going right. So P4 is tension, and it's 1 kip, positive 1 kip. Okay? So that's how I determine my internal forces. So go through this exercise. Okay? You want to make sure you can do this. You can very quickly determine all the internal forces in all your segments. And once you know all the internal forces, then it's just a matter of applying that equation, right? PL over AE. So these are all your P values. L is the length of each segment, again. Area is the area of each segment. And then E is the Young's modulus for each segment. All right, so we're not going to work through the problem. I didn't give you any areas and any diameters or any lengths, right? But you should be able to work through that. So another thing I could ask in a problem like this, okay, I could pick any point on the structure. Okay, I shouldn't have erased the page. Let me see. I could do a redo. Can I not? No, sorry, I lost it. Well, so what I wanted to say was, I'll have to redraw this. I could pick, instead of asking for the overall deflection, I could actually pick some point on this. And most of these problems would be labeled in such ways that you could designate your segments by letters. Like this will be called point A, this will be point B, this is point C, this is point D, and this is point E. Okay? So now instead of referring to these as segments 1, 2, 3, and 4, you refer to this as the force in AB. Right? You would have a force in AB, force in BC, force in CD, and force in DE. Okay? So anyway, right? Another thing I could ask in this problem is I could pick any point other than the ends Like I could pick point D and ask you, what is the deflection at D? Right. How much does point D move and in what direction? Now positive would mean it moves right, negative would mean it moves left, right? If you kept using the left hand as your reference. So how would you solve for this? Well, it's very simple, okay? You still have delta D is the sum of your PL over AEs, except how many terms would you have in that summation? If you say 3, you would be correct, okay? You basically just add up, just like we did if we were finding the deflection at E, the total deflection. You still add up all these terms from segment to segment, except you would only use the first 3 segments. You keep adding up to the point for which you want to know the deflection. Okay, so that's how you would handle that. All right, so that is how you find deflections and how you make use of internal forces and then apply this PL over AE equation. Okay, so let's move on the slides. Here is another example, right? There's a nice one. It's fairly simple, but this will illustrate exactly what you should do, right? And what this problem is going to show you, right, in these 3 segments is you don't always need to use the left-hand side as your reference. If you look at how the book works through this problem, on some of them, they actually use the right-hand side as the reference. You just have to be very careful here. If you're using the right-hand side as your reference, okay, like they do here, you use the right-hand side as your reference, then whenever you get a force, an internal force that pulls left, that is now positive, because now when you use the right-hand side as your reference, you kind of look at the right-hand side as being fixed, and then when you pull towards the left, now you're pulling in tension. So now pulling towards the left is tension, right? If you have an internal force that goes to the right, that would be compression. Okay? That's what changes. Okay? So just be careful with that. And I would always suggest that don't jump around. Don't use the left-hand side as your reference in some problems and the right-hand side as the reference in some other problems. Just stick with something, and that way you don't get confused. Okay? And like I was saying, most people choose the left-hand side as their reference because, okay, that is more consistent with our standard Cartesian coordinate system where you go from left to right, right? You go in the positive direction. Okay, let's move on. I'm not going to talk too much about sample problem 2.1. Okay, you can look at it if you want. This type of problem is actually not very common. All right, so the next thing, okay, static indeterminacy. Now, in statics, okay, you probably talked a little bit about what it means when you have a statically indeterminate situation. So let's just briefly review here. If you have more unknowns than you do have equations, then you're not able to solve your algebra problem. Right? Correct? In the case of static equilibrium, if you look at a 2D case, right, you have 3 equations of equilibrium. Sum of forces x equal to 0, sum of forces y equal to 0, and sum of moments about some point is equal to 0. That's 3 equations of equilibrium. It means you could solve for 3 unknowns. So and usually in statics, you're solving for unknown reactions. So that means you could have 3 unknown reactions that you could solve for. If your problem is supported, right, in such a way that you have more than 3 unknown reactions, then your problem is statically indeterminate. Is it still in equilibrium? Yes, of course. It means you've overly constrained it. You've constrained it more than you need to. Usually in the real world, that's not a problem, right? Because that means you're sharing the forces, the reactions among more supports. It actually makes your structure more robust, right? But as far as the math is concerned, you don't need that many supports. And you're not able to solve for all the reactions, okay? So in statics, we always solve for the minimum case, right? What is the minimum that is required to hold something that's in equilibrium? And once you solve that situation, if you want to add more support in real life, then go right ahead. It actually makes your structure, more stable. But, mathematically, you can't solve a statically indeterminate problem. Okay, not with the methods that you learned in statics. In mechanics of materials, there are actually certain statically indeterminate problems that we can solve. And the reason for that is we could come up with one more equation, okay, in addition to our equations of equilibrium. And that equation has to do with deflections, okay, or deformations, delta. And this is the first type of a statically indeterminate problem that you're going to encounter, okay, in mechanics of materials. So before we get into the actual problem itself, right, you'll see on this slide here that I talked about superpositioning, right? This word, superposed. So there's a principle that is extremely powerful that's used throughout mechanics and materials. It's referred to as the principle of superposition, as you might imagine, and it's something that you could do in Newtonian mechanics. Okay? The great thing about Newtonian mechanics is that if you have a bunch of different things that are going on a structure, meaning if I have a bunch of different forces that are applied to a structure, and I want to know what the effect of those forces are, then there's no need to look at all those forces together. Okay. Superpositioning says you could look at one force at a time, try to determine what each force is going to do to your structure separately, and then once you've determined all the separate effects, you add them all together to find the overall effect on your structure. Again, this is something that you could apply whenever Newtonian mechanics applies. And that means pretty much everything we're going to be doing in mechanics of materials. So let's talk about how this really works in the problems that you might find. Let's go to the next slide. Our statically indeterminate problems are going to be something like this. You have something that's very similar to the problems that we just looked at, right? You have a composite rod. It's made up of a bunch of different segments. You have forces being applied throughout that rod, that composite rod. But now, instead of having one end free and one end fixed, both ends are fixed. You're going to fix both ends. And in statics, you would not be able to solve that problem. So if you look at this example here, what would you be asked to find in statics? Well, the only unknowns are the reactions at the two supports, correct? And how many reactions is that? Well, this is, again, just one dimension. Right? It looks like a two-dimensional problem, but if you look at it, all the forces are in the y direction. So there's only one equation of equilibrium that you could use. It's sum of forces y is equal to 0. If you look at this, it's obvious there are no moments, right? And of course, there are no forces in the x direction. So there are no x reactions and no moment reactions at your supports at A and B. So you've got one equation of equilibrium, namely sum of forces y equal to 0, and you have two unknowns, your y reaction forces at A and B. So one equation to solve for two unknowns. This would not be something you could solve in statics. But in mechanics of materials, because we could make use of our deformation equation, this is something you can use. This is something you could solve. And the way you're going to do it is through superpositioning. So how superpositioning works in a problem like this, right, is as follows. You break this problem down into as many statically determinate problems as you need. Okay. And in this particular case, you're going to break this down into two statically determinate problems. So how do you determine which two statically determinate problems? Well, the way you superpose, okay, is you're going to look at a bunch of different categories of effects. And what I mean by that is this, okay? External forces or applied forces are one effect. They cause some kind of reaction, some kind of, they're gonna cause something to happen in your structure, right? Anytime you have applied forces. And by applied forces in this problem, I'm referring to the 300 kilonewton force at D and the 600 kilonewton force at K. Okay? So I'm going to look at the effect of those two applied forces by themselves. I'm going to look at what those two forces by themselves is going to do to this structure. And then what is the other type of effect that's going to happen? Well, there's a reaction at A and a reaction at B, right? When you have those two reactions together, reactions are essentially forces. Reactions are external forces. They're not applied, but they're external. Okay? So I have to look at the effect of those applied forces. Those reaction forces as well. And those are the only two things that are going on, right? I have applied forces and I've got reaction forces. So I need to separate out what effect those two categories of forces have. Okay? And the way I do that is to separate this out into two different statically determinate problems. The first statically determinate problem is basically looking at the applied forces. And if I want to look at just what the applied forces want to do to this structure, I have to allow this structure to deform freely. And the way I allow it to deform freely is to remove either the support at A or the support at B. So in our particular case, we are going to remove the support at B. Okay? So that's this middle figure here. Let me draw that. That's this. Okay? That is the first statically determined problem. Can everybody see, right, that this problem is statically determined? Right? The reaction at A is the only unknown now, and it's going to be 300 plus 600. That's 900 kilonewtons, right? And it has to be 900 kilonewtons up because the 300 and the 600 are down. All right? So that's one effect I look at is the applied forces. The next effect I look at is the effect of the supports. Now, if I want to look at just the effect of the supports, I've got to forget about everything else. So I forget about those applied forces, and now I just look at the effect of those reaction forces. And the way you're going to do this is, if you removed the support at B in the first part, now you're going to look at what effect the reaction at B actually has. Okay, so that's this last figure here, where I remove the 300 and the 600 kilonewton forces, and I just look at this reaction at B. I don't know what value that is, right? But I know there is some reaction. And, you could either assume it's tension or compression. It doesn't matter, right? In this case, we just assume that it's pushing up. Okay? And once you do this, you're going to solve those two problems separately. So let's go and look at how that's done. Okay, go to the next slide. This is the first problem. All right, so like I said earlier, you're going to solve for the reaction first. That's 900 kilonewtons going up at A. And now you determine how many segments there are. Remember, this is a problem now very similar to the one that we did a few slides ago. So how many segments is this? Well, remember, pick a reference. Let's pick A as our reference. So pick A as our reference, and then I start going down, all right? At point D, I encounter an external force. So from A to D is one segment, right? Then I go from D to C, I encounter a change in area. That's another segment. From C to K, there's a change in force, right? So that's another segment. And then from K to B, you actually have another segment. But if you were to work this out mathematically, okay, you would find that the internal force in KB is 0. And the reason that's so is because in between K and B, right, there are no more external forces. There's no external force at B. Okay, so your force at B is 0. I mean, another way to look at this is make a cut between K and B, right? Do you need any force at that cut to have equilibrium? No, because the 900 kilonewtons going up is already balanced out by the 300 and the 600 kilonewtons going down. So the internal force in KB, again, is 0. So even though there are 4 segments in this problem, you only need to sum up 3 terms in that summation. Okay, so you have PL over AE for those 3 segments. You add it up. You're going to get some actual value for the deformation. Right? You're going to get a delta is equal to something. And that delta is going to be the delta at B, the free end, right? The total deformation. Okay? So here's how you work that out. Right? That's using the right-hand side as a segment. Those are all the internal forces that you can see. Right? You notice that this is 0, 0, then 600, 600, and 900. Right? And you're just going to add up your sum PL over AEs. All the areas are listed, right? The lengths are listed. Okay? And you get this. E hasn't been plugged in yet, right? But that's the total summation for the deflection at the free end. And then you go to the next problem. The next problem is this. How many segments? So if you take a look at this, right, what is the reaction at A? Well, the reaction at A must be equal to this RB, right, in order for you to have equilibrium. So because in the first part I removed the support at B, in this part of it, what I'm trying to find is the reaction at B. Okay, so the reaction at A is also equal to RB, and then I start moving down, right? I'm going to use the top as my reference again. Notice that you just have 2 segments. What is the internal force in each segment? It's just equal to RB, right? And because I assumed RB as compression, notice I put in the negative sign, right? That's me assuming a direction, and if RB ends up being positive, then I assumed correctly. If it ends up being negative, I assumed incorrectly. Okay, so notice now when you sum up your PL over AE, you don't get a value. You get something in terms of RB. RB is an unknown. Okay, so let's go down to the next slide. So what do I do with this now? I've got 2 results. Okay, from that first problem, I've got delta is equal to some value. In the second problem, I've got delta is equal to something times RB, my reaction at B. So once you've solved each of those individual problems, the next step, okay, is based on what actually happens physically. If you look at this problem, right, we said that if we remove the support at B, then B is going to deflect by some amount, right? And then the reaction at B will cause it to compress by some amount. Well, in actuality, is B going to deflect? No, right? This structure is fixed at both ends, at A and B. So this structure cannot deform at all at A or B. So what that means is, even though I've separated out into two different effects, and each effect is going to result in some deflection at B, what is the overall effect? The overall effect is that the deflection at B must be 0. All right? So what that means is I'm going to take this. This is the deflection at B, if there was no support at B, then I'm going to take this, right? This is what the reaction force at B wants to deflect B by. And then I'm going to combine them together. I'm going to say those two deflections added together must be equal to 0 because B physically cannot move. Okay? And if you solve that equation, you'll notice that the only unknown is RB. Okay? So you solve for RB, and there it is, 577 kilonewtons. Once you know what RB is, then you go back and solve the statics problem. You're going to go back, right? That's 577 kilonewtons. You're going to go back and say RA, right, minus that 300, minus that 600, plus the 577 has to equal 0 because this is still in static equilibrium. Okay? And once you have that, now you can solve for RA. RA is 323 kilonewtons. Okay, so go ahead and go through this exercise if you didn't follow it correctly or exactly, right? Make sure that you can do this. Make sure you know exactly how to solve one of these problems because I can guarantee you that you're going to see this on an exam at some point. All right, what else can I ask you in this problem? Once you know what RA and RB are, what else can I ask you? I could ask you to find the stress in every single one of these segments. Okay, so let me draw this problem. You've got this was 300, I believe, kilonewtons. This was 600 kilonewtons. Right. And then RB was 577 kilonewtons. RA was 323 kilonewtons. I could ask you for the stress in every one of these segments. Okay? So, how do you do that? Remember, stress is P over A. It's the internal force in each segment divided by the cross-sectional area of each segment. So what that means is you need to know or find the internal force in each segment. So as a review, right, how would you find that? I'm going to use the top as my reference. You could use the bottom if you want, right? But since this problem was worked out using the top, let's continue using the top, right? And then I make a cut here. What is P in that first segment? It's, well, if you make that cut, right, there's the 323, and then I make that cut. I must have 323 up. What is that? That's compression, right? Can everybody see? If this top is my reference, and then I push against that, then that's compression. So it's 323 kilonewtons negative. Okay? How do I find the internal force in the second segment? I make a cut here, right, in the second segment. Make a cut there. So there's the base. That's 323. I now must account for that 300, right? So the internal force here must be 623. So P2 is negative 623 kilonewtons. Okay. How about the third segment? Well, it's the same thing, right? I make the cut there, and there's really nothing that's changed. So P3 is also negative 623. I'm sorry, I messed up here, didn't I? That 323 was up. I drew this incorrectly. It's up. So I apologize for that. Okay, so let's see. So this is positive. Okay, and this was down. Let's redo it. Let me redo this. Okay, so P1 is 323. Let me leave out the kilonewtons. We all know that this is kilonewtons. And it's positive because it's tension. P2, okay, is when I make the cut here. So I've got 323 up and 300 down. I need another 23 down. That's tension. Okay? P3, I've got the same thing. It's 23 positive. P4, I've got 323 up, 300 down, 600 down. I need another 577 up. That's compression. So minus 577. Okay? So these are the internal forces. And now when I want to find the stress in every one of these four segments, I take each of those internal forces and divide by the area of each segment. Is that clear? All right. So that is a statically indeterminate problem. Okay? And you want to get used to these problems because, as I said, you will have this on your exam. Let's move on. Okay, now we're going to talk about the effect of temperatures. When you heat something up, I think pretty much everybody knows that the material will expand, right, if you heat it up. And when you cool something down, then it contracts. The amount of expansion or contraction intuitively depends on the temperature, right? But it also depends on the material. And what people have found through experiments, just like with Young's modulus, right, just like with the ultimate stress, is that the reaction or how much expansion or contraction that you get with the temperature change is a material property. And the way we're going to express this material property is by something called the coefficient of thermal expansion. Here is your next Greek letter. Okay, Greek letter alpha is your coefficient of thermal expansion. And the units for this are given as per degree, either Celsius or Fahrenheit. So what does that mean, right? It's some value per degree Celsius. Well, if you remember, strain is dimensionless. Okay, so what that means is your coefficient of thermal expansion is actually a strain per degree Celsius. Right? How much strain do you get in your material when you increase or decrease your temperature by 1 degree Celsius? So if you look at the typical values for coefficient of thermal expansion, they're very small. Okay? Materials do not expand all that much with 1 degree of temperature change. In fact, it's almost nothing, right? You need very large temperature changes on the order of like 100, 200 degrees Celsius to get any noticeable amount of expansion or contraction. Okay? But the fact of the matter is every material has a coefficient of thermal expansion that you can look up in the materials properties tables. Okay? If you want to see it for yourself, go flip to the materials properties table in the back of the book. You will see it listed, okay, in both the table for SI units and the table for US units. So how does this play into the materials that we're looking at? How does this affect our work with the materials we're looking at? Okay. Well, first of all, okay, if you have a material, some piece that you're going to heat up by some amount delta T, okay, then it's very easy to actually determine how much strain you end up with in the material. Remember, alpha is it's actually a strain per degree Celsius or degrees Fahrenheit, right? And that means if I want to find strain, I just take alpha and multiply by the change in temperature. Okay? And what is strain? Strain is delta over L. So if I want to find the actual amount of elongation or contraction due to a temperature change, I just multiply by L. It's alpha delta T times L. Okay, so that's how I determine how much something is going to stretch by or something is going to shrink by when you apply a temperature change. Right? You simply look up its coefficient of thermal expansion. You take that coefficient of thermal expansion, multiply by the change in temperature, multiply by the original length, and you will get the amount of deformation. So how are you going to apply this? Well, very easy, right? If I give you a temperature change now, along with everything else in the previous problems, then all you need to do is apply superposition again to determine the total amount of elongation. So if you go back to that problem that I drew up a little earlier, right, where we had 3 segments. Right, and then we had these forces that we were applying. All right, if you remember that. Now, instead of having just this, I could say that there's also a temperature change. So we had said this was 1 kip, right? This was 1 kip, 1 kip. This was 3 kips. And now in addition to that, I add a temperature change of, let's say, 200 degrees Fahrenheit. Okay? And I ask for the total deformation at that free end. How would you work through this problem now? Well, you still have delta due to forces. That's the sum of PL over AE, right? That's the problem we worked out earlier, or at least we discussed how you would work this out earlier, okay? But you now also have a temperature change. So your delta, or your deformation due to delta T, is going to be the sum of your alpha delta T L. So what that means is you're just gonna have these 3 extra terms, right? Now 3 terms, you have 4 terms here. Remember there were 4 segments, but here there are 3 segments because you don't worry about the applied forces. You have 1 segment here with 1 alpha value, 2 there, and 3 here. Okay, so you add up those 3 additional terms, and there's your overall deformation. Good. But what if you have a statically indeterminate problem? So before we get into that, okay, let's talk a little bit about what happens, right, if you have this piece, if you've got a rod, let's say, and you hold it fixed. You hold it fixed between 2 plates. You have this rod, you're going to hold it fixed between 2 plates, and then you increase the temperature. What's going to happen here? This rod wants to expand, right? It's going to push against those supports, but those supports are not going to let it expand. So what happens? A force develops, okay? And the forces, of course, result in a stress within this rod, but you end up with reactions at those supports. Right? So you end up with a stress. Is there going to be a strain in this axial direction? No, right? Actually, those supports, of course, are keeping it from expanding. So there's no strain, but there's a stress. The funny thing is, right, if you have a situation where you're not fixing your rod on both ends, you just fix it on one end and you apply a delta T, do you have a strain? Yeah, right? You increase the temperature, this thing just stretches, so you have a strain. So this is very funny compared to what happens when you apply forces, right? When you apply a force to a rod, you get a stress. But look what happens here. When it comes to forces, a stress results in a strain. So you can't get a strain without a stress. But in these two cases here, dealing with temperature change, if you look at the bottom case, is there a stress if all you apply is a temperature change? There's not, right? There are no forces. So even though there are no forces, you end up with a strain. So in the bottom case, you get a strain without a stress. How about in that top case? In the top case, there's no strain because this rod cannot elongate, right? It's being held in place. But you end up with a stress. So now you have a stress with no strain, right? And in the bottom, you have a strain with no stress. This would not happen with forces, right? With the forces, in order to get a strain, you must apply a stress. If you apply a stress, you must get a strain, right? So how do you kind of consolidate these two different situations? Well, it's actually quite simple, okay? All you need to do is look at a temperature change as another way of loading your part. Okay, so if you look at delta T as having the same effect as applying a force, now it makes sense, right? And the top case becomes like a statically indeterminate problem, right? You're applying a load, a delta T, right? And even though there's no overall strain, there is deformation like in the middle, right? You just don't get an overall deformation. And then on the bottom case, if you apply a delta T, which is a load, then you end up with a strain. Okay? So now it's actually consistent with what happens when you apply a force. Right? You could either apply a force or you could apply a temperature change to get a strain. All right, so how do you account for a temperature change now in a statically indeterminate problem? Well, remember superpositioning? You just need to account for that temperature change in your superpositioning. And here's how you're going to do it. All right, so let me come up with a problem here. I don't believe there's one in my slides, okay, but let's just double check. No, this is a very simple superpositioning. Okay, so let's come up with a problem. So let's not make this overly complicated. If you know how to work out a fairly simple problem, I mean, a more difficult problem is going to be similar, okay? Just mathematically more tiresome. Okay, and let me give Let me give some values here. Let me see. Let's say AB is half a meter long. BC is also half a meter long. All right, CD, let's say, is 0.8 meters long. ABC is one material, right? And let's say its Young's modulus is 50 gigapascals. And then CD, let's say, has a Young's modulus of 100 gigapascals. Coefficient of thermal expansion, let's say alpha is, what are typical coefficients of thermal expansion? They're all 10 to the negative 6 power. And I don't know, let's say this is 10 times 10 to the negative 6 per degree Celsius. And this is 5 times 10 to the negative 6 per degree Celsius, right? And the problem is going to say, find reactions. Okay, and then let's find stresses, the stresses in each segment. Okay? So how are you going to go about this? Well, superpositioning obviously is the method that you need to use. How many problems do you break this down into in the superpositioning? Let's think about this. Right? Remember what I said earlier? I said in superpositioning, you look at the effect separately of all the different types of things that you have going on. Basically, all the different types of loads that you have going on. Okay. So the types of loads that you have in this problem, I forgot to put in the temperature change. Let's put in a temperature change of 200 degrees Celsius. Right. So the different types of loads that you have going on are the applied forces, that's the 10 kilonewtons and the 220 kilonewton forces. Then you have the effect of the reactions, okay? And now you have the effect of the temperature change as well. So you need to break this down into 3 different problems. So let's add a page. All right. So the first problem that we have, let me label this 1. The first problem is to look at just the effect of the applied forces. And the way you're going to do that is you just remove one of your supports. Okay? So my applied forces were 20, 20, and 10. Right? So 20 kilonewtons, 20 kilonewtons, 10 kilonewtons. And it's fixed here. I'm going to remove the support on the right and use the left as my reference. Okay, so that's the first problem you're going to solve. And why don't we go ahead and solve this, right? This is, or at least let's get started on it. I'm going to say delta at, this was A, B, C, D, right? So delta at D is equal to the sum of PL over AE. You know, one thing I forgot to give you are diameters, right? So let's see, ABC, let's say this is a diameter of 0.2 meters, and then let's say this is a diameter of 0.1 meter, okay? Because I need areas, and usually you would be given a diameter, okay? So, what are your internal forces? Well, first you find the reaction at A, right? What is the reaction at A? reaction at A must be 30 kilonewtons going left. Right? So let's find our internal forces. Internal forces in AB. Right? If you make a cut between A and B, you must have 30 kilonewtons at that cut, and that 30 kilonewtons is going right. So that's tension. It's 30 kilonewtons. Okay? Then your P at BC, your internal force in BC, as you make a cut there, now you've got 30 and 10 both going left. At your cut, you must have 40 going right. That's 40 kilonewtons in tension. And finally, okay, in CD, do you have anything? Think about it. If you make a cut between C and D, okay, you've got 40 going left and 40 going right already. So P in CD is equal to 0. All right, so delta at D is equal to 30 times 10 to the third newtons, right, times the length of AB. If you look back on the previous page, that was 0.5 meters. Area is pi times radius is 0.1 meters squared. And E, what did I put for E? E was 50 gigapascals. Okay? 50 times 10 to the 9th pascals. Okay? That's 30. Then I have BC, that's plus 40 times 10 to the third. Now I'm going to leave out units. Okay? Make it a little more concise. Over pi, it's the same area since ABC are the same rod. It's just that there's a force being applied at B. Okay? So 0.1 squared. And then same Young's modulus, 50 times 10 to the 9th. Okay, so if you work this out, you're going to end up with some value. There's going to be some value here. Let's skip that. Okay, what I would suggest you do is go home and finish this problem on your own. Fill in all the blanks. Okay, so that's the first part of the superpositioning. Okay, delta D, and look what I'm going to do here. I'm going to put this as delta sub D sub 1. That's the first part of the superpositioning. What is the second part of the superpositioning? Now we're going to look at the effect of the support. Okay, so that means I remove everything else. And what effect does the support have? The support is going to take on the form of a force. So let's assume it's compressive. We might end up being wrong, but we don't know that for certain, right? So this is my reaction at D. Okay, and I remove the internal forces. So this is the second part of the superpositioning. And what is going to be my reaction then on this end? Well, it's got to balance out that RD, right? So this is RD as well. What am I going to get from my internal forces when I make my two cuts? It's going to be RD compression, right? So delta at D of this part is PL over AE, where each internal force P is a negative RD, right? And now length, I just used that whole length, A, B, C. Okay, so 0.5 and 0.5 is 1 meter. Over A, that's pi times 0.1 meters squared. And E was 50 gigapascals, 50 times 10 to the 9th pascals. Okay, then minus, this is now CD. That was 0.8 meters. Pi times, the diameter was 0.1 meters, so radius is 0.05 meters. And then Young's modulus was 100, I believe, right? 100 GPAs. Okay, so that's the second part of the superpositioning. This is going to give me delta is equal to some value times RD. RD is an unknown. Okay? What is the last part of the superpositioning? It's looking at the effect of the temperature change. Okay, so I did put in this subscript 2 there. So now we're looking at the effect of the temperature change, and what that means is I forget about that support, forget about the effect of the support, forget about the effect of the applied loads, and I simply look at delta T is equal to 200 degrees Celsius. Okay, so 2 segments again. And now I'm going to get delta at D, right, part 3. This is going to be the sum of alpha delta T L. And what were my alphas? My alphas were 10 times 10 to the negative 6 and 5 times 10 to the negative 6. Okay, let's go all the way here. Okay, so 10 times 10 to the negative 6, 10 times 10 to the negative 6 per degree Celsius times 200 degrees Celsius times a length of 1 meter. And notice this is a positive temperature change, it's a temperature increase, so obviously it's going to cause positive deflections or positive elongations, right? Plus 5 times 10 to the negative 6 per degree Celsius, 200 degrees Celsius, 0.8 meters. And this again is going to give me some value. Okay? And what do I do with all of this now? Now I'm going to combine everything together. I'm going to say delta at D from the first part plus delta at D from the second part plus delta at D from the third part has to be equal to 0, right? Everything is fixed. So point D, or the end of that rod, cannot move whatsoever. If you think about this, this was a number, this was a number, this was something times RD. So when you solve this equation, that's going to give you RD. Okay? And then how do I find RA? You're going to say sum of forces equal to 0. That will give you RA, because now you know what RD is. RA is the only unknown. Okay? And once you have all of these forces, how do you find the stress in each segment? Well, you go back and make those cuts, right, to find the internal forces. And once you have the internal forces, just go ahead and divide those internal forces by the areas, and that will give you all your stresses. Okay, so hopefully this illustrates exactly how superpositioning is going to work. Okay, and this is probably as difficult as it gets when it comes to these statically indeterminate problems. Okay, so you have to be able to handle cases where you have a temperature change, applied forces, and then you have statically indeterminate structures. All right, so this is going to be the end of part 1 of this week's lecture. Okay, I am going to post up another video with more. Okay, and that's going to be in a separate YouTube video, because I am getting pretty close to a very large file here for this first part. Okay, so let me sign off here and be on the lookout for the second video, which will cover the rest of chapter 2. Okay, so let's end this right here.